Good afternoon, dear colleagues. My name is Pономарева. Let me introduce our paper called OIP Concept as a Basis for Business for Analysis of Multidimensional Data Structures. Large organizations currently apply several thousand management decisions daily. Expansion of production capacities and the market for sales of goods and services, reputation management, brand management, is only part of the directions of development of organizations that increase the number of decisions made and consequently increase the volume of information flows necessary for managers to effectively manage within the areas of professional responsibility. The received information is becoming more and more heterogeneous. The consideration of indicators requires more and more inclusion of additional information for a comprehensive analysis. At the same time, the admissible decision-making time is preserved and often even reduced. The problem of the rapid increase in the volume of heterogeneous information necessary for making managerial decisions served as a trigger for search for a technology that allows you to quickly process the summarized information coming from different sources and bring it to decision makers in convenient form with possibility of detailing the received information. The main problem of obtaining analytical indicators for organizations managers in this paper is the speed of obtaining such information. The problem is related to a number of features. A large amount of initial data in the used databases, loading of databases by other processes, cross queries to different tables and databases, the need to apply mathematical operations to the query results, and data preprocessing. The following questions were posed during the study. The first question is how to increase the speed of obtaining analytical indicators for making managerial decisions when working with big data. The second question is how to ensure the relevance of the obtained analytical indicators, and the third question is how to demonstrate different analytics based on user needs. The answers to these questions will lead us to the development of a concept for the transition from requesting data as a request of user to requests within periods specified by the frequency of updating information and requirements for relevance, as well as performing all necessary calculations with storing the results of calculations of analytical indicators. At the same time, a new request for indicators coming from the user decision maker doesn't refer to data sources, but to the storage of already calculated indicators distributed in the context of vectors useful for user analytics. This is exactly what the OIP concept offers. Let's move on to the research methods. OIP technology is used as a developed concept of working with big data. OIP, online analytical processing, is a concept that describes the loading and storage of analytical indicators using a specialized intermediate layer, data cube, hypercube, that stores data using a multi-dimensional structure. The scheme of operation of this technology is shown in Figure 1. The most familiar view for a single slice of hypercube can be considered the view of a pivot table, inside which numerical indicators are distributed over several categories of a nested structure. The technology itself in most of the market has found application in business intelligence systems as the most modern way of reporting. That is why users often don't even think about organizing data transfer from the source to the system itself when re-engineering reporting as a channel for receiving management information using BI systems. The technology, as a rule, involves internal storage of data using hypercubes, and the process of setting them up is developed by system suppliers on design stage. To deepen their understanding of OAP, consider the following case. An organization of mining industry uses a BI system in its activities to monitor analytical indicators used to make management decisions by organization managers. There is a centralized database that collects data on actual production and indicators necessary to predict production opportunities in future periods. There are also a number of interfaces, REST APIs, counterparties that provide data on predicted demand for an organization's products. In addition, the HR department of the organization collects information on the number and academic performance of students from the faculties of local universities who carry out educational activities in specialized areas on the basis of which it is possible to assume the supply of the labor market for planning the expansion of the organization's staff. It is also possible to obtain accounting data to obtain indicators of the economic activity of the organization. For example, let's take data only on production and production opportunities. A simplified diagram of the organization's database is shown in Figure 2. Figure 2 shows that some divisions are assigned warehouses of industrial equipment necessary for the development of a new area, 5 types of equipment. You can also see the connections of the divisions parcels. New areas can only be mined if another area is being mined next to them. According to the results of the monthly production, the subdivisions record the production for the period for 3 types of extracted resources. Suppose who might need these data. For example, when predicted increased demand for extracted resources in excess of the current production capacity, the regional manager must decide to develop new areas of the division. For him, it is important to understand the level of demand from counterparties by territory with distribution over time, current production capabilities by territory, the possibility of increasing optimal production capabilities in distribution by enterprises and geographically. The indicators required by him can be presented in the form of tables presented in Figure 3. In this form, the data is stored already with required aggregation, which means that when requesting indicators, we don't need to make new requests to data sources and aggregate them. They were obtained earlier. Next, the data structure describes the levels of detail of indicators. Note that the tables of predicted demand and the cost of products of the demand are quite close in terms of the information stored in them. However, demand disaggregated by categories, location, resource, prediction date, and cost by categories, location, prediction date, resource. This is because it may be useful for us to study the predicted demand for a certain resource in dynamics, but the revenue that we receive is more interesting in the distribution by months and within months, already by resources, and depending on the analysis tasks that we set, the order of categories can change. We also note that the cost of the production volume that satisfies the predicted demand is calculated not only in terms of resources, but also in terms of dates. At the same time, looking at the table of possibilities for expanding production capacities, we can say that for a high price of received information, it would be possible to calculate separately the share of the ability to meet demand with current capacities for individual decisions to calculate the percentage of excess production and other indicators. In other words, on its basis, you can form a number of cubes, each of which will carry more useful information. Also, the example shows that the name cube doesn't create a requirement for the need to use 3 categories as dimensions. There can be as many categories as you like, depending on the requirements for detailing information. After analyzing the tables, we can formulate a number of conclusions that come from Figure 3. These simple queries to the generated hypercubes are enough. The received data is brought to a single format, doesn't require additional operations. If mistakes occur in the process of loading data from sources, they can either be processed or its processing doesn't occur. Do not overwrite the data obtained during the last loading of data from the source. A request for obtaining data from sources is made according to the schedule and not during the user's session. Now, data storage requires some amount of disk space in addition to the initial data. However, using of random access memory has been significantly reduced. In view of the possibility of obtaining data from different sources, it is inappropriate to talk about uniform practices for entering data into an LLP system. However, getting data from a hypercube structure has several characteristics that you can see on this slide. As a practical application of OLP technologies, as a rule, people talk about the directions of budget policy, data analytics, as well as the storage of consolidated reporting. Regarding the application of technology in business, they usually cite analytics in the areas of marketing, purchasing and sales, tariff and pricing policy, as well as monitoring as a control tool using threshold values of analytical indicators. Currently, OLP technology is widely used in analytics and data consolidation systems. So, in addition to BI systems, OLP technologies have found application in accounting support programs, organization management systems, and CRM systems. However, BI systems and accounting information systems are still considered to be the largest coverage. At the same time, the potential of the technology can be called not fully disclosed, since even in those situations where multidimensional data storage is required, more familiar relational databases are often used. It should be noted that the concept of proactive data acquisition has become more often implemented in modern IT projects. However, even now, there are IT projects in which user requests for primary data are still being made for reasons of saving disk space. Thank you for your attention.